Assalamualaikum guys, today we'll be presenting aeronautic wing design for fuel efficiency. The group members of the project constructed by four. First is Irfan, Zahirul Haq, Zahrul, and Ain Aisha. Introduction to aeronautic wing design. Aeronautic wing design for fuel efficiency is all about making airplanes as sleek and aerodynamic as possible, helping them glide through the air with minimal resistance, ultimately saving fuel and making air travel more eco-friendly. So first thing first, we need to aim to design wings that generate the right amount of lift to keep the airplane in the air. Second is minimizing the drag, which is the resistance the airplane faces. Third is less drag, means the airplane doesn't have to work as hard and therefore it requires less fuel. And the last one is it involves considering the size, shape, angles, and material construction.
There are seven parts to study about the wing design. The first part is the aerodynamics. Aerodynamics diminish air resistance, contributing to heighten the flight efficiency, and also ensuring engines and associated components are integrated in a manner that minimizes the drag while maximizing the thrust. Like you can see in the picture, the use of computational fluid dynamics CFD simulation as demonstrated with the Boeing 787 Dreamliner plays a crucial role in honing wing design, minimizing drag, and maximizing lift for improved fuel efficiency. The second part is the airfoil design. Airfoil design induces lift by manipulating the air pressure differential as it interacts with the surrounding airfoil. It helps steering and controlling the aircraft motion and managing the complex forces at play in aerodynamics. Like you can see in the picture, there are 6 types of airfoil design. There are early airfoil, later airfoil, clockwise airfoil for subsonic, laminar flow airfoil for subsonic, circular arc airfoil for supersonic, and double wish airfoil also for supersonic. The third part is the wing sweep. Wing sweep are measured along the mean aerodynamic chord to determine how air flows over the wings during flight. By calculating the wing sweep, we can know how to increase sweep contributes to streamline airflow and reduce drag at higher speed. It is ideal for supersonic and hypersonic flight. Fighter jets favor significant sweep for agility and speed, while commercial airlines often for more moderate sweeps to accommodate a range of operating conditions. Like you can see in the picture, there are 6 types of wing sweep. The first one is tapered leading edge, straight trailing edge. The second one, tapered leading edge and trailing edge. Delta wing for one swept back wing. The fifth, straight leading and trailing edges. And the last one is the straight leading edge, tapered trailing edge. The fourth part is the aspect ratio. Higher aspect ratios lead to lower induced drag. Higher aspect ratios distribute lift more efficiently across the wings, resulting in reduced drag. Like you can see in the picture, this is the glider ASK21. During cruising phases, allowing this glider to cover greater distance with less fuel consumption. The fifth part is the winglets. Winglets used to reduce vortices and induce drag, enhancing fuel efficiency, particularly during cruise. Like you can see in the picture, how winglets diminish the resistance. Winglets cut drag and boost fuel efficiency by shrinking the vortex of air at the edge of plane wings. The left box is how conventional wingtip produce large vortex, so the more drag. And the right box is how smaller vortex produced when using the blended winglet, so less drag. The inward, upward, and slightly forward lift components of the upper airfoil, the new lower airfoil generates a vertical lift component that is vectored away from the fuselage and also slightly forward. Working together, this provides the perfect balanced winglet that maximizing the overall efficiency of the wing. Part number 6 is wing materials. Wing materials for aircraft are selected based on the specific functions of different wing parts. Aluminum alloys, titanium, or carbon fiber composite used for main structural components like the spar and wing box. Composite materials used for wingtips, winglets, and the internal components due to their strength to weight ratio. Titanium alloys used for aerial engines and experiencing high temperature. Last but not least, Part 7. Flaps and slats. Flaps and slats enhancing lift during takeoff and landing, preventing stalls at low speed, improving maneuverability, reducing required takeoff and landing distance, increasing drag for controlled distance, optimizing fuel efficiency. Like we can see in the picture, how additional lift caused by Coanda effect. This helped by the extended slat and extended flaps. How the air moves to the wings from the chord line, the high angle of attack. This helped improving the maneuverability.
Now, I want to talk about the calculation of aeronautic wing design for an aircraft. An aircraft's overall performance and fuel economy are greatly influenced by its aeronautic wing design. To maximize aerodynamic performance, fluid mechanics theories, concepts, and equations are applied during the design process. Here are some important fluid dynamics related aeronautic wing design elements, along with pertinent equations and theoretical ideas, in aerospace engineering. First of all is lift and drag calculation. This section has 4 equations that lift force, drag coefficient, induced drag coefficient and drag coefficient at zero lift. The first one is L equal to 1 over 2 CL rough V square A. Secondly, CD equal to D over rough AV square over 2. Thirdly, CDI equal to CL square over pi ARE. For the last equation is CD equal to CDO plus CDI. For this equation where L is the lift force, CL is the lift coefficient, rough is the air density, V is the airspeed, A is the wing area, CD is the drag coefficient, D is the drag, CDI is the induced drag coefficient, AR is the aspect ratio, E is the Oswald efficiency factor, and CDO is the drag coefficient at zero lift. Next we go to the aspect ratio and induced drag. This section has 2 equations. Aspect ratio, AR, is the ratio of the wingspan to the mean chord average width. High aspect ratio wings tend to reduce induced drag and improve lift-to-drag ratio. The lift-induced drag, DI, can be approximated using the equation. DI equal to CL square over pi ARE multiple with rough A versus square over 2. Finding the wingspan, or the distance between wingtip to wingtip, and the area of the wings are 2 methods for calculating the aspect ratio. Next, divide the result by the wing area after multiplying the wingspan by itself. Span square divided by area equals aspect ratio.
Next, challenges in aeronautic wing design for fuel efficiency. First, implementation cost. Advanced material and cutting-edge technologies in wing design often comes with highest initial cost. Research, development, and production of innovative materials can be expensive, impacting the economic feasibility of widespread implementation. Second, maintenance challenge. Utilizing cutting-edge material may require specialized maintenance produce and training for maintenance personnel. Implementing new technologies may introduce complexity in maintenance routine, potentially leading to increased operation costs. Third, technological risk. Due to introducing novel materials and technologies carries inherent risks related to reliability, durability, and overall long-term performance. Ensuring the safety and reliability of these technologies become crucial, requiring extensive testing and validation processes. And fourth, transition period. The aviation industry may experience a period of adjustment and adaptation as it shifts from conventional to advanced wing design. Pilot, maintenance crew, and other stakeholders may need additional training to effectively operate and maintain aircraft with innovative wing technologies. And the last is advantages of aeronautic wing design. First, Optimize wing shape. With advanced tool and simulation, enable the identification and implementation of wing shapes that minimize drag and maximize lift. Will improve aerodynamic efficiency, lead to reduced fuel consumption, enhancing overall aircraft performance. Number 2, surface coating. Innovative surface coating such as laminar flow technology maintain smooth airflow over wing surface. Reduce surface friction, minimize drag, leading to increased fuel efficiency and improve aerodynamic performance. Number 3, winglet integration. Effectively reduce wingtip vortices, dimension-induced drag that can be improved fuel efficiency and increase lift, especially during cruising phases of flight. Number 4, lightweight material. Utilizing lightweight and high-strength materials such as advanced composite reduce the overall weight of the wing. Reduce aircraft weight translate to lower fuel consumption and increase payload capacity, contributing to improved efficiency. And the last, flexible wing design. Adaptability in wing design allows for dynamic adjustment based on varying aerodynamic conditions during flight. Optimal wing performance throughout the flight envelopes enhance fuel economy and overall efficiency.